So my name is Akang Wang. I'm from Shenzhen Research Institute of Big Data in China. And this is work with Linxin Yang, Sha Lai, and Professor Xiaodong Luo. And also colleagues from Huawei, including Xiang Zhou, Haohan Huang, Shenchen Shao, and Yuanmin Zhou, and Dong Zhang. So here we are facing we have a mixed MLP, mixed integer linear programming problem. The decision variable is XY. And the vector C, D, H, and the matrices A, B are representing parameters. So maybe we have lots of these instances, maybe these parameters are following some distribution. So the key question is whether we can utilize ML machine learning to enhance or speed up the optimization step. And as Dr. Kasim point out, we didn't rely too much on the machine learning algorithm. We use classic OR techniques, but we also use simple machine learning techniques to tune parameters in our Primal heuristics. So we focus on the Primal task, and we want to minimize the Primal integral here. And we have 3 data sets: item placement, load balancing, and anonymous. So for each of them, we rank for the first in the competition. So we have for each instance, for each data set, we have a specialized approach. So let's focus on them one by one. So first, item placement. So for the item placement, from the training instance, we know that for each instance, they are like 105 items, and they are 10 containers. So we want to assign items to containers. And for each container, there are 3 dimensions. So basically, it's a multi-dimension, multi-knapsack problem where you want to assign an item to a container. Then you have the knapsack constraint, the sum aik times xij less than equal to bk. And also you have another knapsack constraint like the one following, but you are penalizing the violation of the knapsack constraint. So you have a sum d xij plus yi greater than equal to 1. Here, the key the discrete verb is xij, whether you assign item I to container j, where continuous variable y and z are representing the penalty. So from the across all the instances, we collect the statistics. We found out that there are in total 105 items. For the first 100 items, the size is much smaller. While for the last 5, their sizes are much larger. They're significantly larger, actually. Specifically, for the last 5, their A and D value, they are close to 1. So if we go back to the formulation, if for the Y constraint, for this one, if D is close to 1, you don't want to put 2 more items into the same container. Otherwise, you are wasting Y, because we are penalizing 1 here. So with a key observation here is that we can apply a symmetry breaking constraint. Specifically, we can assign the last 5 items to each container respectively. So we assign the last 5 items to the first 5 containers respectively, one by one. So that's the first thing, first observation. So using this, so we apply this first. Then we rely on MetaHeuristics and the MetaHeuristics. So specifically for MetaHeuristics, because it's a knapsack problem, it's fairly easy to construct a feasible solution. So we use a classic greedy heuristics. Then after that, we rely on large network search to improve the heuristics, the solution. For the masked heuristics, we have 2 steps, two approaches. One is a construction approach. We call this 2-step approach. Basically, we already put the 5 large items into the first 5 containers. Then we want to figure out for the small items, for the item 1 to item 100, for the first 100 items, we want to figure out which of them should be assigned to the first 5 containers. So we solve like a relaxed problem. So we assume if an item is assigned to the last 5 container, we assume their sizes they have continuous size. Basically, we relax the integral constraint for those items. So we solve a relatively easy assignment model. After that, we want to figure out for the last 5 containers, we want to, how do we assign items? So after that, we solve a submip. So using this 2-step approach, we construct the first solution in the MetaHeuristics step. Then after that, we use a fixed optimized idea. Is basically for the remaining 5 containers, we choose 2 container, we define a submip, we optimize. That's the basic idea for the first problem. Then for the second one, it's a load balancing. We have 60 tasks, 100 machines, and this is basically the model. We want to minimize the number of used machines. For this model, so I don't want to go to the details. The key observation here is, let's say we solve the linear program relaxation. We relax the integrated constraint. We solve the linear program relaxation. We get a feasible solution. Well, if we round up, so here y is the only discrete variable. So if we round up y, we will all guarantee get a feasible solution. Because when you round up y, all the constraints are satisfied. Then when you round up, you also have the you also satisfy the integrated constraints. So you always have a feasible solution. Okay. Then after that, we also realized, because if yj is 0, xij will always be 0. So we can tighten the model a little bit. Basically, here we say sum xij less than equal to bj times yj. Originally is less than equal to bj. Okay, so we do this tightening, and at the same time we can also, because of we have this new tightening constraint, we can remove the original constraint xij less than equal to aiyj. It's guaranteed to be valid because bj is always less than equal to ai in this data set. Okay, so we have a tightened formulation. This formulation is much smaller and have a tighter, and this formulation also has a tighter ALP relaxation value than the original model. Okay, using this, so we rely on rounding heuristics to find feasible solution. So in the very beginning, because the E. coli environment provides us with LP solution, root LP solution, we use it first. Then after that, we solve the tightened model. We get the linear relaxation model. We also use the rounding heuristics based on that solution. Also, we do a little bit sophisticated thing here. We use a binary search and use some quantum selection methods to select the threshold value. We don't just do simple rounding. We choose some thresholds to round. So there's some, we apply this many times, but it's very, very efficient in this step. Then after this, we rely on RANS, which is very classic primal heuristics. We use the Titan model based on the second LP solution. Okay, that's for the second problem. So for the first one, I have 1 minute. Let me just finish. For the last one, we don't know the problem formulation very well because it's an anonymous problem, and we realize that the model formulation, they are not very exactly the same, at least from our understanding, from our observation. Also, the problem size changes. But a key observation we have here is that we realize it's something related to inventory problem, inventory management, something like this. So we can define a planning horizon. We can figure out the planning horizon actually, and for each discrete variable, we can associate them with a time period. For example, for day 1, this discrete variable is associated with day 1, and this variable is associated with day 2, something like this. Then first, to get the very first solution, we rely feasibility pump. This is the classic primal heuristics. We rely on feasibility pump. Then if we get the very first solution, we return. And at the same time, we also use RANS to improve the solution. Basically, we fix, let's say we know the planning horizon is 100 days. For the first 90 days, we fixed all the discrete variables at the incumbent solution. Then for the last 10 days, we relax, we solve the submip. Okay. Then after that, to further improve the solution, we utilize a rolling horizon idea. It's basically for the whole planning horizon, let's say for 100 days. For the first, let's say 10 days, the solution is all the discrete variables, they are fixed. Then for the last, let's say 30 days or 50 days, all the constraints involving those discrete variables, they are ignored. Then in the middle, lots of continuous variable, there are lots of discrete variable, they are relaxed to continuous. Then we only have a very small amount of integer variable. It's a very small size MILP we can solve. Then we move we increase h hat, h bar, and h tilde until the very last moment. And then at the same time, we fix more variable. So a few constraints will be ignored in the end. And then in the end, we will produce a feasible solution, hopefully. Okay, to summarize, we have three problems for each of them. For the first two, we utilize some OR and modeling ideas, and then after that, for each test we have the construction methods and the improvement methods. Specifically for the item placement, we utilize MetaHeuristics and the MetaHeuristics, and for the other two, we use the classical OR Primal heuristics, but also we're using data-driven ideas here. Thanks for your listening, and that's all. Thank you.